Okay, I wasn't sure whether I wanted to use hats or tildes or W's. I was kind of leaning toward W's, and that's what your book does. That's what we're going to use for these vectors, okay? So we're going to say that our calculation scheme. W2, which is going to replace V2, is this orthogonal vector, okay? So we're going to say W2 equals V2 minus the projection of V2 onto V1. Okay? And for the moment, we're going to let W1 just equal V1. Now really what we're going to want is we're going to want to normalize these. We want them all to be unit vectors because they're really easy to work with. But right now we're going to be content just to make them orthogonal, because then all we have to do is divide them all by their magnitudes. You have what we call orthonormal basis. Okay? So normalizing is real easy. Once you have the vector, you just divide it by its magnitude. So we're not going to worry about that. But this whole thing about projections. Okay? Now what do we have? Okay, well let me write it down, that W1 equals V1, then W2 is going to be this, right? Okay? Now I could explain it geometrically, but for the moment take my word for it. If I then take V3 here and subtract its projection onto W1 and its projection onto W2, I'm left with something that's perpendicular to both of them. Okay? So I'm going to say W3 equals V3 minus the projection onto, and now I'm going to use W1. I probably should have used W here. Okay? And V1 and W1 are the same. And now, let me use this. Of V3. And what that does is it takes any component of V3 that's not perpendicular to V1 and removes it. And then remove the component of W2 that isn't perpendicular to remove the component of V3 that isn't perpendicular to W2. That makes sense? Now you haven't proven it. But intuitively it should make sense, and it should make sense of the process. Okay? We'll go into a little more detail about exactly how that works, and we'll prove it. But let's just do it first. Okay?